Okay, hi everyone, welcome back to part 2. And now that we saw examples of group actions on vector spaces, orbits, and orbit closures, let's explore a little bit the geometric questions that arise, the geometric and computational questions that arise from group actions of vector spaces. Okay, so, now we saw that given 2 points U and W in our vector space V, do their orbit closures intersect? Right? So that's the first geometric questions that we already talked a little bit about in the first part of the lecture, right? And this is a very natural question to explore, right? Either from a mathematical perspective or even from a computational perspective, right? So we'd like to decide whether two orbit closures intersect. And if W is actually equal to 0, so if one of the points is actually equal to 0, we get the null cone problem, because now if W is equal to 0, then the orbit of W is just 0, which is equal to the orbit closure of W, right? So then the orbit closures intersecting, right? So the orbit closure U intersect the orbit closure of W is equivalent to just asking whether 0 is in the orbit closure of U. Right? So then we get what is called the null cone problem, which is given just the vector U is 0 in the orbit closure of U. Okay? And this problem is called the null cone because it gets its name from the definition that given a group G acting on a vector space V, the null cone of this group action is the set of all elements that have 0 in their orbit closure. Okay? So this is the definition of the null cone. This is the null cone. Okay, and this was defined by Hilbert in his foundational work in 1893. Okay, so all right, and the orbit closure containment, okay, is the other problem that, you know, if we had, as we saw before, like there are two orbit closures, they can intersect, right, in case of the conjugation action, but they may not be, one orbit may be fully contained, one orbit closure can be fully contained in the orbit closure of the other one, right? So as we saw, like the orbits do not intersect, but the orbit closures intersect, and actually one orbit closure contains the closure of the second orbit, right? So we'd like to know as well, if given 2 points U and W in the vector space V, does the orbit of U contain the orbit closure of W? And my apologies, this should have been a U here. Okay, so all right. And another question that we would like to ask is, well, given a point U in V, is the orbit of U actually closed? Okay, does U define a closed orbit? Because if you remember, like in the conjugation action, the identity is a closed orbit, right? So we would like to know, it would be nice to decide if an orbit is closed, right? Okay, so, all right. And then here, let's see a little bit. So now we're gonna focus a little bit in the null cone problem, okay? Because as it turns out, the null cone problem already has a lot of applications in computer science, functional analysis, combinatorics, and also its statistics, as we're gonna see in lecture 5, okay? So from now on, we're gonna explore the null cone problem. And why is the null cone problem very, very important in mathematics? Is, for instance, if we have the change of coordinates like of bivariate polynomials, like of bivariate forms of degree D, it turns out that the null cone, okay, so this is the null cone problem is exactly the problem of deciding whether a polynomial has a multiplicity has a root of multiplicity bigger than D over 2. Okay, because here the null cone is exactly the set of polynomials P, X, Y of degree D, right? Such that P has one root of multiplicity D over 2. Okay, and if you think about it, for instance, if you have like d equals to 2, the null cone here is exactly the polynomials p of xy, okay, such that the discriminant of p is equal to 0, right? Where delta here is the b squared minus 4ac. Okay, so where if you think of p as the polynomial ax squared plus byx plus ax squared plus bxy plus cy squared. Okay, so this is exactly, if the discriminant is equal to 0, we know that the polynomial, this polynomial can be written as like, you know, alpha x plus beta y squared, right? So if you have a multiplicity bigger than 1, which means you just are a square of a linear form, we know that you're in the null cone. Okay, so the null cone captures quite important objects there. And now, if we have, for example, the left multiplication, which computationally, this left multiplication action, you can think of it as Gaussian, the action that one gets by Gaussian elimination, or by, yeah, let me put Gaussian elimination, or like, to be more precise, like row reduction, right? So row reduction of matrices. And here, the null cone, okay? So the null cone of this action is exactly the set of singular matrices, okay? So it's a quite important object. So you know now the set of matrices of determinant 0, they're actually a null cone of a group action, okay? And now if we have the conjugation action, it turns out that for this action, the null cone is exactly the set of nilpotent matrices. So again, we're seeing that quite important examples of special types of matrices, they actually correspond to null cones of certain group actions, okay? So they're geometric objects, right? And when we talk about row and column scaling, and if you remember, this is the matrix scaling action, right, that we talked about, matrix scaling. Okay, what we get actually is that we here get that the null cone is the set of graphs can be encoded by graphs without any bipartite matching. Okay, so this should be like weighted graphs. Okay, so we should be weighted with complex weights. Sorry, let me actually weighted and bipartite. So weighted bipartite without bipartite matching, right? So, okay. And now, if we, one other problem that has a lot more applications as well is that if instead of having two special torus matrices, okay, we didn't define this action, and we're not going to talk much about it, but I will refer to the workshop lecture notes for you to look up more about operator scaling. Okay, so if you have the action of now two, let's say here we have L and R. These are two matrices, like this is an element of G, of our group G. So L and R are two matrices in SLN. And now our element of our vector space is a tuple of matrices A1 up to AM. Okay, this is in V. And now the action is that you multiply all these matrices A1 up to AM simultaneously on the left and on the right. So we're going to have L A1R up to L AM R. Okay, this is called the operator scaling action. Okay, which you can think of simultaneous left-right multiplication. Okay, so this group action actually captures the word problem for free skew fields in non-commutative algebra. Okay, it captures the problem of rational identity testing in algebraic complexity theory, and it also captures proving that certain inequalities in functional analysis, which are the well-known Braskamp-Leib inequalities, that generalizes all the inequalities, that essentially all the inequalities that you know in functional analysis. It characterizes whether there is an inequality or not. Okay, so okay, and if you're interested in learning more, there has been a lot of developments algorithmically on all of these problems, and the development is exactly because of the application of these geometric invariant theory techniques to these problems. Okay, so all right, and now you may ask, okay, how do we know that the null cone of each of these actions are these objects that I'm actually describing to you, right? And okay, now let's go back to the origins of the null cone, right, by the works of Hilbert in 1893, where he defined the null cone. Okay, so Hilbert in 1893 actually said that the null cone, if you remember, what was the definition of the null cone? So the null cone is the set of all elements of the vector space such that 0 is in the orbit closure of U. What does that mean? It means that there's a sequence of group elements that takes U to 0, right? Like that makes U converge to 0. And Hilbert actually proved that the null cone is the 0 set of all the non-constant homogeneous invariant polynomials. Okay, and an invariant polynomial, okay, so an invariant polynomial, which I did not define, and I'll define now. What is an invariant polynomial? Is a polynomial that, so it's a polynomial, let's say, P, V, which is actually in the coordinate ring of the vector space V. Okay, so it is in the coordinate ring of the vector space V, is invariant if and only if, like, P of V is equal to P, even after I apply G, the action of G in V, for every element of the group G. Okay, so P is an invariant if and only if P does not change, right? And here's an exercise for you to check that you already know many invariants. Okay, so you already know many invariants. Exercise. So for instance, the discriminant delta, which is b squared minus 4ac, is an invariant polynomial for the action of SL2, which acts on, let me just put the symbol for, like, SL2 acts on the vector space V of polynomials of degree 2, right? So this is homogeneous forms of degree 2, like binary forms of degree 2, right? So Hilbert proved in much more generality that the null cone for these group actions is the 0 set of all of the non-constant homogeneous invariant polynomials. Okay, so, and later, like, Mumford also generalized this to the orbit closures. Okay, so what Mumford proved is that two orbit closures intersect, right, which is on this left side. So we're saying here is that orbit closures intersect, okay, if and only if all the invariants, so this right side is saying that all invariant polynomials evaluate to the same value on U and W, right? Which means that for any invariant polynomial, if you evaluate on U and W, you must get the same value. Okay. So in particular, one good thing about these theorems is that this problem, so the upshot, what is the upshot here? Is that null cone, like orbit closure intersection problems, and the null cone is one of them, right, can be captured by polynomials, by invariant polynomials, right? So that's really nice. And one is tempted to use algebraic approaches to actually solve the null cone problem in the orbit closure intersection problem. And those approaches have been quite successful as well, okay? But they become quite difficult quite quickly as well. And okay, so for instance, again, if we talk about the action of SL2 on the linear transformations of forms, the invariants are the discriminants, okay, and also more polynomials, right? Whenever D increases, we have more invariants, okay? And for example, if we have the left multiplication action by SLN, an invariant polynomial here is the determinant, okay? And it turns out that the determinant generates all the other invariants, okay? So the determinant is essentially the unique invariant, like if you have the determinant and the constant polynomials, all the other invariants are polynomials over the determinant, okay? And if you talk about the conjugation action, what are the invariants of this conjugation action? So it turns out that the invariant polynomials for the conjugation action are the trace polynomials, okay? And when we talk about the matrix scaling action, what it turns out is that the invariant polynomials here are exactly the matching or permutation monomials, okay? So, so here it turns out that all of these actions, they have very easy polynomials, which are actually very helpful in describing the null cone as well, okay? And to characterize the group action. So, okay, now we saw all the orbit closure intersection problems, and you may ask, okay, what about orbit closure containment? Okay, so orbit closure containment seems to be a much, much harder problem, okay? And in particular, the central problem in algebraic complexity theory can be formulated, okay, which is the P versus VNP question. So this is the algebraic analog of the P versus NP question, okay? So the central problem in algebraic complexity theory is actually an example of an orbit closure containment, okay? So is an example of orbit closure containment problem. Okay, so, and this is the central problem in algebraic complexity theory, right? And there has been very little progress towards this general question. And okay, and why is this question so important? It's important in many areas of mathematics, actually. And this question, the VP versus VNP question, asks whether the permanent polynomial can be efficiently computed by an algebraic circuit, okay? And it turns out that this has implications de-randomization and complexity theory, okay? And in other parts of also of algebraic geometry as well, okay? So, all right. Now, let's talk about the null cone from an optimization perspective, okay? So let's take it from an optimization perspective, from a more geometric perspective, right? We saw now the algebraic perspective where we had the polynomials. We looked at it through the viewpoint of invariant polynomials. And now I would like to talk about an optimization way of viewing the null cone problem, right? So with the null cone, we want to know whether 0 is in the orbit closure. So when our vector space has an inner product, and suppose that our vector space is like C to the n, so we definitely have an inner product space, right? This motivates the following question, right? So take the infimum over all the elements of the group of the norm of the action, like G acting U, right? And here the norm is the norm induced by the inner product. Okay, and now well, since the null cone is really interesting only when the group is infinite, right? So let's not consider anymore like finite groups, because the null cone for finite groups is just like 0, because all the orbits are closed. Okay, so 0 is the only point in the null cone. So now whenever we talk about the null cone problem, we talk about continuous groups. Okay, so this is the norm induced by the inner product. And we have now this optimization question that arises from the null cone, right? And okay, and now, but here, one complication is that, well, we usually just know convex optimization. And here, somehow we have an optimization over the group elements, right? So this, and the group may not define to us a convex set. So we cannot try to hope to do like convex optimization right away, right? So it turns out that this geometry of this optimization problem, the geometry of this problem is actually determined by the geometry of the group, because now we're like optimizing, right? So if you think about it, what we're doing is we're optimizing a function. We're taking the infimum of some function over the group elements, right? And G and G. So this is the type of problems that we're trying to solve now, right? So we need to know now what is the geometry of the group, right? To determine how to solve, if we can actually solve these problems in an efficient way. Okay, so, all right. And now if we just recap the orbit closure. So then, since the problems of orbit closure containment was really hard, let's just focus on the orbit closure intersection. And in particular, let's just focus on the null cone problem, right? So to recap, the null cone problem was, if I give a point U in V, is 0 in the orbit closure of U, right? So this is the problem that we're interested now. And here, right, now we were faced with the following question, right? So, okay, there is an optimization problem that's related to the null cone, right? Or we may ask, okay, so we have that optimization problem. Can we use that optimization problem to solve the null cone? Well, we saw that, well, if we had a list of all invariants, if we could list all the invariants, we could try to use Hilbert's theorems and just say, okay, evaluate our point in all those invariants, right? And if in one of these invariants I don't get 0, I know that my point is not in the null cone, right? But somehow, like, it would be nice to have a geometric way to approach such problems, because in many instances, the invariants are hard to obtain. And if the invariants are hard to obtain, we cannot hope to have efficient algorithms for these problems. But if we have a geometric way to approach such problems, it could be the case that we don't need to evaluate all the invariants, right? So like to bypass having invariants, right? And try to solve this problem without evaluating on all the invariants. So again, when our vector space has an inner product, we were motivated by the following optimization question, right? We had, which I'm gonna call the capacity, okay? So this is the capacity of an element of the vector space. So the capacity of U is the infimum of this optimization problem, right? And now we know that U is in the null cone if and only if the capacity of U is equal to 0. Because if the infimum of this optimization problem being equal to 0 is exactly equivalent to saying that there's a sequence of elements in the group that make, like, there's a sequence GT in the group such that GT, when I act on U, this tends to 0, right? So this is exactly, this problem exactly captures the null cone problem, okay? So in the next lecture, we're going to see how to devise and analyze efficient algorithms for the matrix scaling, okay? So here, what we have, we're gonna start showing to you a little bit of this very general theory of how to solve efficiently these scaling algorithms, okay? And in the next lecture, we're going to see how to devise and analyze efficient algorithms for matrix scaling. But matrix scaling, I just want to warn you, that is a commutative action, right? And what do I mean by a commutative action? I mean that the group G, the group is commutative, okay? So, and these actions, actually, we can use convex optimization to solve the null cone problem. We can use just standard convex optimization to solve such problems. Okay, so that's good. But then the question will be, what happens when the groups do not commute? And then we're also going to devise algorithms in this workshop. We're going to show you how one can devise algorithms that can also solve the null cone problem in many situations of interest. Okay, so all right, yeah, in lectures 3 and 4, we're going to see how to solve scaling problems for non-commutative group actions. Okay, so to conclude, what did we see today? So today we learned the basics about geometric side of invariant theory, and we saw many examples of important group actions and their geometric problems, right? We saw how they have connections to many other areas of mathematics. We learned a little bit, right? We just saw an overview of fundamental problems and theorems in geometric invariant theory. And we just described a little bit about scaling, like basics about scaling algorithms. And we saw that the optimization viewpoint is very natural in geometric invariant theory questions. Okay, so in the next lecture, Akshay is going to teach you scaling algorithms for matrix scaling. Okay, and this will be for commutative group action. And in lectures 3 and 4, we're going to see scaling algorithms for non-commutative group actions. Okay.